Hello, I am Alex Kavner, and I will be discussing measuring the samarium-146 half-life utilizing absolute decay counting. I was a PhD student at the University of Michigan under Professor Igor Ivanovich and a LRGF fellow at Lawrence Livermore National Laboratory under Dr. Yanbo Kim. I worked on cryogenic detectors as part of the ultraspec detection group. In this talk, I will discuss magnetic microcalorimeters, the decay energy spectroscopy technique, the controversy of the samarium-146 half-life, and the techniques we developed to remeasure said half-life. First, magnetic microcalorimeters. These are radiation detectors which measure the microheat of individual radiation interactions. The detectors are comprised of a radiation absorber, a thermometer, and a cold heat bath at tens of millikelvin. When radiation interacts with the absorber, a change of temperature is induced proportional to the energy deposited. The cold temperatures of the heat bath allow for superior resolution to other detector technologies, such as scintillation crystals or high-purity germanium detectors. To measure the temperature, a spin state comprised of a gold foil doped with erbium-166 is developed. The magnetization or average spin of the erbium-166 is dependent on an external magnetic field and the temperature of the system. This means that the magnetization forms a direct measurement of the temperature itself. Through a series of induction coils and quantum amplifiers, we can read out the average spin state and thus the magnetization and the temperature of the system. This is an example of a detector where on the lower left you can see the gold foil containing the erbium-166 sputtered onto a chip. This chip is then wire bonded to a quantum amplifier, and the wire bonds to the PCB provide electrical connections both for biasing the detector as well as reading out signals. So the decay energy spectroscopy technique differs from traditional radiation detection, whereby instead of an external source, the nuclear material is embedded within the absorber itself. This allows 4-pi encapsulation and hence 100% counting efficiency, as well as the high resolution of KeV at the MeV scale. This is multi-vectored and is sensitive to alphas, betas, X-rays, nuclear recoils, shake-off electrons, etc. For actinides as well as samarium-146, this allows us to measure the decay energy and hence Q spectroscopy or decay energy spectroscopy. On the right, we see a gold foil containing nuclear material wire bonded to the previously shown MMC and squid setup. To encapsulate the source, the nuclear material is dissolved within a solution. This solution is deposited onto the foil. The foil is encapsulated, rolled, and pressed, and then wire bonded to the detector. On the right, this is the experimental setup with the gold foil containing the samarium-146 wire bonded to the gold pixel of the MMC. The primary spectroscopy advantage over say, alpha spec is that for species with multiple branching ratios, these are all combined into a single peak. For example, for plutonium-239, there are 3 primary alpha peaks, whereas when it is embedded within the gold foil, we see a single peak at the decay energy. If we know the number of atoms deposited onto the gold foil and we can measure the number of counts within the decay peak, we can reconstruct the activity, and hence the half-life can be calculated as the ratio of the number of atoms to the measured activity. So the samarium half-life controversy. Why samarium-146 is important is it is a part of the samarium-neodymium counting system. This nuclear chronometer is used to measure the half-lives or to measure the ages of various solar system samples, such as meteorites, moon rocks, and Martian crust. It works via the long decay of samarium-147 with a 106 billion year half-life and the short decay of samarium-146. This allows us to well constrain the timescale of solar system formation. However, errors and uncertainties in the 146 half-life results in systematic uncertainties in age estimations. The reason why there is a controversy is the two prior measurements performed by Meissner and Kinoshita differ by about 35 million years. This is a challenging measurement because samarium-146 isotope is extinct. You have to produce it via an accelerator or a reactor, which produces other 146 isomers. It is typically low activity. There are beta impurities with endpoints higher than the 146 Q value, and any detector has low efficiency, hence why we want to use Q-spec. The Meissner measurement utilized an absolute decay counting technique utilizing pips, whereas the Kinoshita measurement measured relative 146 to 147 isotope decays. Traditional modern detector technologies are subpar for this measurement. PIPs and silicon detectors employ low efficiency and source attenuation due to surface level. Liquid scintillator has high backgrounds and poor resolutions. Ionization chambers have no resolving power, and mass spectroscopy can't be used alone to determine a half-life. Hence, this motivates the Q-spec experiment. So our experimental procedure, a 146 samarium sample was produced at the Triumph in one of their accelerator beam lines. It was purified at Lawrence Livermore National Laboratory. An aliquot was taken from the solution to measure the mass and the number of atoms. The remaining solution was deposited onto a gold foil and encapsulated within said foil, wire bonded to the detector and counted. And then post the counting measurement, the gold foil containing the solution was redissolved and the samarium was extracted for a second mass measurement. The techniques developed are discussed in the publications on the lower left. We had to develop several modeling and data analysis procedures because the signal response of microcalorimeters is slow, usually tens or even hundreds of milliseconds. Cryogenic detectors usually use custom-built analysis software. This is because each pulse shape is unique depending on the thermodynamics of the system. And due to these slow response rates, counting activities are usually limited to sub-becquerel measurements. Therefore, pileup complicates any counting experiment and has to be accurately characterized, as well as we had to develop an analysis technique. We chose a trapezoidal filter based on that used in high purity germanium detectors, which allowed us to perform counting with minimal distortions and due to pileup, though several modifications had to be made, notably in the pole zero correction, whereas while high purity germanium detectors exhibit one decay time, there are multiple in cryogenic sensors. We performed several experiments with alpha and samarium 147 sources, where we then salted the data by injecting a known number of simulated pulse shapes at random timestamps and measured the distortion to the peak shape at various count rates and pileup conditions. This allowed us to come up with a correction model to reconstruct the detection efficiency from the count rate itself. We also worked to develop several source preparation techniques. This was done with samarium 147, as 146 is precious and we didn't want to waste any of our solution on these development techniques. So we purchased 147 with a better known half-life and performed several experiments. We typically observed ugly peak shapes with partial energy deposition steps. These were assumed to be flat, however, were observed to be increasing in low portions of the energy spectrum. This was found to be caused by slow rise events, where we would see a population of fast events corresponding to the full decay energy, whereas we would see lower energy slow events whereby the full energy was not reconstructed. We found that these were usually due to crystallization of the source, whereby precipitates on the foil would form around the decays and act as heat sinks, similar to charge trapping within high purity germanium detectors. To counteract this, less source material was used. This was naturally achieved, as while we used micrograms of samarium 147, nanograms of 146 would be used. A larger source area, a larger foil where the source could be more evenly distributed throughout the foil would be used, as well as thicker foils, which would allow us to better encapsulate through pressing and kneading of the gold material. This sacrificed energy resolution due to the greater heat capacity, but allowed better encapsulation of the source material itself. So finally, the 146 samarium measurement. The source was successfully deposited onto the foil. We performed two counting experiments with different levels of preparation. One where the foil was simply folded over itself, labeled experiment one, and then a second round where it was rolled with a mill. And we did this to continuously monitor the activity and pulse shapes. During the first experiment, we saw a fast tail. We attributed this to events on a layer of gold higher up, and therefore fast with a faster connection to the sensor itself. And then in the lower plot, after more processing of the gold foil, the peak improved in resolution, and we performed the activity analysis on both areas. We counted between 2150 and 2750 keV and kept that the same as to minimize systematic effects from changing this integration window on the foil. We estimated the background usually by linear interpolation, though we accounted for differentiating background levels with different models and included that in our uncertainty estimation. We found that the background model was best fit by a power law spectrum. And again, the difference between the power law and the linear interpolation of the background were included in the analysis. The only contamination we saw was samarium 145, which decays via electron capture, which likely was produced and at the accelerator and captured as samarium 145 hydride. On top of the samarium 145 in environmental backgrounds, we found a samarium 146 of 20.161 millibecquerel with sub 1% uncertainty. In the combination of the two experiments, we had 26,500 samarium counts. Minimal numbers of events were cut, mostly due to dead time, event selection, and background estimation. The majority of the events cut came from being within the end zones of the continuous acquired data, which was separated into 10-second segments. Multiple analyzers looked at the data and found consistent results between experiment one and experiment two, and the spread in the data was statistically analyzed, whereas the spread was of only a 1 sigma difference, and thus is within the statistical uncertainty. I performed several statistical analyses looking at the spacing of events, the fit of Poisson distribution, and found consistent activity numbers to the 20.161 value. The number of atoms was assessed to be 7.88 times 10 to the 13. This was done via the radiochemistry groups at Lawrence Livermore National Laboratory, and the half-life was found to be 85.76 plus or minus 0.65 million years from that number. A simultaneous experiment by another collaboration at the Paul Scher Institute performed a similar measurement utilizing traditional PIPS technology, and they came up with a slightly disagreeing value. However, their error bars are significantly larger due to the aforementioned uncertainties of silicon detectors. However, we can say that the spread in measurements has shrunk to a much smaller degree. These programs were funded by the DOE NNSA LRGF, the Consortium for Monitoring Technology and Verification, as well as Lawrence Livermore LDRD funding. Thank you for listening.